Let's now talk about another type of stereoisomer that is actually a carbon atom which contains 4 different ligands in which there exists an identical mirror image of that molecule, and that is called chirality. So stereochemistry based on chirality. Molecules, like objects, sometimes have handedness. Let's first look at objects. Handedness is like the right hand and left hand. If I take my right hand and I take my left hand and I try to superimpose them, meaning I'm trying to bring them into each other, I notice that they're non-superimposable. That's because they are mirror images of each other. So hands are non-superimposable mirror images. An object whose mirror image is non-superimposable onto itself, we call that chiral. If we have objects that are mirror images but they are superimposable, for example, an object would be like a chair here. If I look at its mirror image, I could slide this chair right into this chair. They would superimpose right into each other. We call those achiral. So we can have the same thing with molecules. If I look at this molecule on the left and I look at its mirror image, if I were to slide this molecule over into this one, notice that they are not superimposable in each other. If I slide the 1 over to the 1, that's fine. If I slide the 3 over to 3, that's fine. But the 4, when I slide it over this molecule, it's superimposable onto the 2. So, and the 2 would be superimposable on the 4, and so they're not the same. So this would be considered a chiral molecule. These two molecules are non-superimposable mirror images of each other. Therefore, they're chiral molecules. They're stereoisomers of each other. The criteria for a chiral molecule based on carbon is that I have a carbon atom that has 4 different things attached to it. Okay? So if I have a carbon atom that has 4 different things attached to it, and there exists a mirror image of that molecule that is non-superimposable, these two are stereoisomers of each other. So if we look at the carbon itself, we sometimes call that a asymmetric carbon atom. We also sometimes call it a chiral carbon atom, or we can also call it a stereogenic carbon atom. Those are just 3 different terms used to describe this carbon with 4 different ligands sticking off of it. So let's check for stereoisomers here. Are the molecules mirror images of each other? Yeah, they're mirror images of each other. I put a mirror plane down between them and sort of they reflect each other. Are the molecules non-superimposable? Yes, they're non-superimposable. Therefore, they are stereoisomers of each other. How about a compound? So a chiral compound is has a non-superimposable mirror image. An achiral carbon has a superimposable image. So let's look at these 2 molecules here. If I look at this molecule, notice that these atoms and this carbon and this bromine are all on the plane of the board. This methyl group is coming out of the board and this hydrogen is going in. So if I draw the mirror image of it, you can see that this mirror image, if I try to superimpose them now, they're non-superimposable, because if I drag this molecule over to this molecule, they don't map into each other. So this is a chiral molecule. It's got a chiral carbon. They are non-superimposable. Therefore, these 2 molecules, they're different molecules. They're stereoisomers of each other. If I look at this molecule, and I look at this carbon, 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 and bromine, they're all in the plane of the board. I have a hydrogen going back into the board. I have a hydrogen coming out of the board. I take a mirror image of it, and notice now I could actually superimpose them. If I rotated one of these 180 degrees, I could get these hydrogens to superimpose on these hydrogens. The same thing with the ethyl group and the bromine. In fact, these molecules, with a little manipulation from my brain, are superimposable. In fact, this carbon is not chiral either, right? It does not have 4 different things attached to it. It's got 1, 2, and these hydrogens are the same, so it's only got 3 things attached to it. So these two are identical molecules of each other. They're identical compounds. They're not stereoisomers of each other. Whenever we talk about stereoisomerism, we tend to compare one molecule with another molecule, look to see if there's a chiral carbon, look to see if they're mirror images of each other, look to see if they're superimposable on each other. So let's look at the chiral carbon specifically on this molecule. And we oftentimes, as you might have noticed in some of those other slides, we've put an asterisk around the chiral carbon. Let's look at the other carbons here. This carbon here, it contains 3 of the same atoms. These are representing 3 hydrogens here, so that's not chiral. This carbon has 2 hydrogens on it, so it's not chiral. This one has an ethyl group, a bromine, a hydrogen sticking back to the gourd, and to a methyl group. That is chiral. A methyl group is different than an ethyl group, is different than a bromine, is different than a hydrogen. So if I have a chiral carbon, there exists another molecule that's the mirror image of it, and I can draw that right over here. So these 2 molecules are non-superimposable mirror images of each other. No matter how I manipulate this molecule by twisting it and turning it in space, I can't superimpose it on top of this molecule. This is a good opportunity to take out model kits and make the 2 stereoisomers and try to superimpose them. It's a little bit hard looking at 2-dimensional space here, but the model kits, and if we were in lecture in person, I could show you this very easily. Here's another way to represent that molecule. And so here I've just drawn the lines and dashes. These atoms here are all in the plane of the board. This bromine's coming out, this hydrogen's going back. These atoms are all in the plane of the board. This bromine's coming out, this hydrogen's going back. And if I do the mirror image of each other, again, no matter how I twist it or manipulate it in space, they're non-superimposable mirror images. Those are stereoisomers of each other. Let's look at the different ways we could depict 2-bromobutane. I could just represent it as the expanded structural formula, recognizing that this carbon has an ethyl group, a hydrogen bromine, and a methyl group attached to it. It's a little bit easier to see here if I draw out the line angle drawing. Notice I have not put in the hydrogen here. So I don't know what is sticking out and what is sticking back. I have not shown stereochemistry. What we like to do, however, is show stereochemistry. If I have a chiral carbon, represented by the asterisk here, I have one stereoisomer where the hydrogen is coming out of the board and the bromine's going back into the board. Here I have another stereoisomer where the bromine's sticking out and the hydrogen is going back into the board. So these 2 are non-superimposable mirror images of each other. Remembering when we look at these carbons and these bonds are all in the plane. This is coming out of the plane of the board, and this is going into the plane of the board. What if we don't know? Okay, on this top drawing, the second drawing here, notice I didn't show stereochemistry. I could actually have both of these in my solution, but maybe I can't separate them. If I can't separate them, we draw this squiggly line instead of a straight line, or instead of a wedge, or instead of a dash. This says I have both stereoisomers, or I don't know which one I have, because this is a chiral carbon. We have a word for these non-superimposable mirror images. We call those enantiomers. It's just a big word that scientists have come up with. So if I have a chiral carbon, represented here on these 2 carbons, I have 2 molecules that are mirror images of each other. They're non-superimposable. We call those enantiomers. Enantiomers are different compounds. They are stereoisomers of each other. Enantiomers have the same physical and chemical properties. I mean, they behave the same. So how do we know which one is which by measuring the chemical and physical properties? We don't. However, they do have different biological activity. One of these behaves differently than the other one in living organisms. Just like that anti-nausea drug, that one of the stereoisomers causes teratogenic effects, and one just is an anti-nausea drug. They have different biological activity. There is one physical property that is different between enantiomers. Enantiomers interact differently with light, and we're going to discuss that coming up here. So this molecule absorbs light differently than this molecule. Other than that, they have the same chemical properties, they have the same physical properties. Let's do some practice exercises. Let's draw 2-bromo-3-methylbutane. Let's draw that. Is there a chiral carbon on this molecule? Yeah, there actually is. On this carbon, I have a methyl group, I have a bromine, I have this isopropyl attached to it, and I have a hydrogen attached to it. So this is a chiral carbon. How about this molecule? Let's see. On this carbon, I have a chlorine. I have a hydrogen, which I haven't drawn in here. And if I go to the right of my ring system, I have a methylene, 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 methylene. That's a CH2 group. If I went to the left, I'd have a methylene, 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 methylene. Those are identical, going each way around that molecule. So this does not have any chiral carbons. If I look at cis-1,2-dichlorocyclobutane, and I look at this molecule, and if I look at this carbon here, I have a hydrogen, I have a chlorine, I have a CH2. If I went this direction, I have a CHCl. So yeah, that is a chiral carbon. If I look at this carbon and I go out, I have a hydrogen, I have a chlorine, I have a CH2, I have a CHCl. So there's different depending on which direction I go. So I do have chiral carbons here. However, if I were to start drawing these out a little more systematically, I could draw the two different enantiomers here. This one doesn't have a chiral carbon, so I can't draw any of the enantiomers. What if I draw the enantiomer here? Okay, it turns out there are no enantiomers, because if I drew the mirror image of this molecule, they would be superimposable in each other. So this is, even though it has two chiral carbons, the molecule itself is non-chiral because it has a superimposable mirror image that I could draw. How about this molecules? These look complicated here. If I look around closely at this first one here, I can see one chiral carbon. This is a CH2, that's not chiral. This is a CH2, that's not chiral. This is an alkene, but there's two hydrogens out here, so that's not either cis or trans. This has got three hydrogens. This is the only carbon that is chiral. So attached to this is this 3-carbon alkene out here. I have a CH2, I have a CH2. I go out a little bit further, I have a CH. I have a CH2 in this direction. So going in two directions, either counterclockwise from my chiral carbon or clockwise from my chiral carbon, there's a difference. Therefore, there are 4 different things attached to this carbon. Okay? If I look at this one's a little harder to look at. If I go out from here, I have a CH, I have a CH2, CH2, and I keep on going around. That's different than I went around this way. It takes a lot of thought to look at those both going counterclockwise. And if I look at this atom, this molecule here, I have 2 chiral carbons because of this alkene right here, this double bond. If I go this direction, I hit a CH. If I go this direction, I hit a CH2. If I go this direction, I hit a CH2, CH2, CH. If I go this direction, I hit a CH2, CH2, CH2. There's differences there. Let's draw the enantiomers now of this one. So I have to have a non-superimposable mirror image. That's actually very easy to do. All I have to do is invert the chemistry here. I have a wedge here. I draw a dash here. That's the stereoisomer. That's the enantiomer, the non-superimposable mirror image of that molecule. This one's a little bit difficult because I have 2 stereocenters here. So I literally, in practice, I just draw the mirror image. So you see if I could bring this one up to here, that would be the mirror image. I've actually inverted this stereochemistry now at both of these, but I'm fixed and rigid here. In this one here, I do the same thing. I just draw the mirror image of it, if I move this whole molecule up to here and drew a mirror plane between them, that's the mirror image. So just looking at these molecules, these two are non-superimposable mirror images of each other. Those are enantiomers. These are non-superimposable mirror images of each other, enantiomers. Again, two stereo chiral carbons in these molecules. If I have one chiral carbon, it's easy to draw the enantiomer. Just invert the wedge for a dash line, and you've made the enantiomer. So chiral centers, okay? Chiral centers are actually include both my carbon-based asymmetric carbon, but I could have a nitrogen-based chiral center also. So these are chiral centers. This is an asymmetric carbon. This is an asymmetric nitrogen, because I have 4 different things attached to this carbon. I have 4 different things attached to this carbon. I could also have alkenes that have stereo centers, because if I look at these two right here, I could have either the cis or trans stereoisomer here, so we call those stereo centers. There are no chiral carbons here. Okay, that's because I have to have 4 different things attached to that carbon to have a chiral carbon. If I look at this molecule as a whole, even though I have 2 stereo centers, I could draw a mirror plane down through here. So this is actually an achiral molecule. If I look at cyclic compounds, I could either have the 2 chlorines on opposite sides, or I could have them on the same side. I have chiral carbons in this case. My whole molecule can also be chiral too if I inverted the stereochemistry either at one of these chiral centers or at both of these chiral centers, because they would be non-superimposable mirror images of each other. So chiral centers versus chiral stereo centers. So let's look at stereo centers and the words enantiomers if I look at cyclic compounds. If I look at these 2 molecules here, I can see that if I drew the mirror image of them, I could literally superimpose one on the other. So this is an achiral molecule. So this is, if I have a cis 1,2-dichlorocyclopropane, that's achiral. If I take this molecule, the trans stereoisomer, and draw a mirror image of that, notice if I were to drag this one over on top of this one, the chlorine would map into the hydrogen, and that's not good. What if I rotated the whole thing around 180 degrees? I still wouldn't come out and be able to be superimposable. So these are non-superimposable mirror images. That's the definition of an enantiomer. So these 2 are enantiomers of each other. I could also quickly look at molecules, and if I can draw a mirror plane inside the molecule, an internal mirror plane, I know that these molecules are going to be superimposable, so this is going to be an achiral molecule. Just noticing that there's a mirror plane in this molecule within the. Let's look at a molecule with 4 chiral centers. If I look at this molecule and I draw a mirror plane between the 2 and I draw the mirror image, I can look at those, and if I try to drag this one over here, it doesn't look like it would be superimposable, but if I dragged it over and I rotated it 180 degrees, it would be superimposable, because I could actually draw an internal mirror plane. If I drew a line right from this carbon through this carbon, there would be a mirror plane, and I angled it a little bit. I could draw an internal mirror plane. I wouldn't even have to try to mentally manipulate it in space. So I know that the mirror image is superimposable, and this is an achiral molecule. If you have a model kit, try putting these 2 molecules together and see if they're superimposable. That will help with the visualization. Now let's talk about the Kahn-Ingold-Prelog rules for chiral carbons. We're going to use the same priority system that we used for the EZ system. We're just going to apply it now to. Let's look at 2 different molecules. On the left-hand side here, I have the naturally occurring alanine. It's an amino acid. I look at this carbon with the asterisks on it. I have a methyl group, I have an amino group, I have a hydrogen, and I have a carboxylic acid attached to it. So I have 4 different groups. I can draw its mirror image. This mirror image is not superimposable on this mirror image. And so these two are stereoisomers of each other. They are enantiomers of each other. Because they're stereoisomers of each other, they are different compounds. We need to name them differently. So we're going to use a nomenclature in this system called the S and the R system to name these. And these are based on the Prelog-Ingold-Kahn rules. This molecule on the left-hand side is called the S-alanine, and the one on the right-hand side is called R-alanine. It turns out we call this natural alanine because life only makes the S enantiomer, whereas the R enantiomer can only be made in a laboratory, and it's very difficult to make this stereoisomer and not make this one. So let's look at the system in a little more detail here. I'm going to use the Kahn-Ingold-Prelog system again because it's the most widely accepted. The first thing I'm going to do is identify if there are any chiral carbons in the molecule, and in this one there is one right down in the center. Then I'm going to assign priorities to each group attached to that chiral carbon, 1, 2, 3, and 4, using the same rules that we used for alkenes. I look for atomic mass, so here's fluorine, then nitrogen, then carbon, then hydrogen. On this molecule to the right, I have this is my carbonyl is highest because I put some fake oxygens on here, some ghost atoms. Here I have a carbon, here I have a carbon, here I have an alkene. I go through the whole systematic way of naming these ligands, and I go 1, 2, 3, 4. And now I need to determine whether these are R and S. So on number 3, I need to work in 3-dimensional space. I need to rotate the whole molecule so that the lowest priority group, the number 4, is always pointing back into the board. So in this case here, you can see I have this generic molecule here, which I've rated based on the priority rules. 1 is up at the top, that's highest priority. 2, 3, and 4. I'm going to rotate this counterclockwise so I can put 4 in the back here. So that you have to do mentally, and it's challenging sometimes. Okay. So once I go get that number 4 priority group sticking straight into the page, I then go 1, 2, 3. I go clockwise 1, 2, 3. If I go clockwise, we're going to call it the R enantiomer. Okay, so if I look at this molecule down here, I could do all that. I could rotate this molecule in space, get my hydrogen pointing right in the back, and I could go 1, 2, 3. This would also be the 2-bromo-butane enantiomer. If I rotate it in space and get my 4 in the back, and then I go 1, 2, 3, going down in order of highest priority, to 2 to 3. In this case, I go counterclockwise, so that's the S enantiomer. If I look at my 2-bromobutane down here, also I can see I've rotated it mentally in my mind, and then I go 1, 2, 3. So I've literally assigned priorities to those group. That's counterclockwise, so that would be the S enantiomer or the S stereoisomer. Notice I've added the S out in front of the name here to distinguish it from the R stereoisomer. So S in parentheses -2 bromobutane. Let's look at both those enantiomers side by side. Both of these are 2-bromobutanes. One is the R stereoisomer and one is the S stereoisomer. If I draw a mirror plane between those two and arrange it in space, those are non-superimposable mirror images, so they are enantiomers of each other. Let's do some practice exercises. Let's identify each asymmetric carbon with an asterisk, so that's a chiral carbon. Let's identify whether the compound is chiral or not, so we're looking for internal mirror planes now. And then let's draw the enantiomers, okay? So let's look at the first molecule here. Yeah, there's a chiral carbon right there. I have a CH3, I have an OH, I have a propyl group, and I have a hydrogen attached to that carbon, so that's chiral. If I look at drawing the enantiomers of this molecule, I just make one a wedge and I make one a dash. Those are going to be non-superimposable mirror images of each other. I don't even have to put them side by side. They're just, I know they are because I have a chiral carbon and one's a dash and one's a wedge. If I look at this second molecule here, I can actually identify that there is a mirror plane right down the middle, but also there's no chiral carbons. Here's a CH3, here's a CH2, here's a CH2, here's a CH3. This molecule has an ethyl group and an ethyl group, a hydroxy and a hydrogen, so it contains two of the same thing. That is a non-chiral molecule. If I look over here at this molecule, I notice that I do have a chiral carbon, and I need to draw it out because I need to show stereochemistry. So in this case, I'm going to use lines and wedges. My nitrogen, carbon, and my carboxylic acid are all in the plane. I've drawn the hydrogen coming out and the CH3 going back in. If I want to draw the enantiomer, just switch these two. And I've drawn the mirror image. These two are non-superimposable mirror images of each other. Therefore, there are chiral molecules. It's that simple. So what if I can't mentally manipulate my lowest priority group? Okay. So for example, if I look at this molecule, oh, my hydrogen is my lowest priority and it's already in back. So I can just go 1, 2, 3. That's going to be clockwise. Okay. So this molecule is going to be R-glyceraldehyde. I'm going to talk about that plus coming up here in a little bit. This molecule, my hydrogen is coming out of the board and I can't manipulate it in my mind to put it in the back. So if I have my lowest priority coming out of the board, I can then go 1, 2, 3. It shows that it's going counterclockwise, and I should call that S, but my highest priority is coming out front, so I know it's got to be the R enantiomer. These two molecules are identical molecules. I've just had to use a sort of a abridged, mentally reversed system for actually naming them, defining whether it's the R or the S isomer, because I couldn't rotate this molecule mentally in my mind. Okay. So we do this when the lowest priority is in front. Okay. Let's do a practice exercise again. Let's go ahead and mark each asymmetric with an asterisk. Then let's designate the asymmetric carbon as either an R or an S. So we have to do prioritization of all the ligands. And then we're going to determine whether it's R or S by going clockwise from 1, 2 to 3 or counterclockwise to 1, 2, or 3. Okay. So there's my chiral carbon. I have a methyl group, ethyl group, hydroxy, and a hydrogen. Is this going to be the R or S? So that oxygen's highest priority, that's number 2, number 3. Ooh, and that's number 4, but my hydrogen is sticking out in front of me. So if I go 1, 2, 3, that's going to be counterclockwise. But I know because my lowest priority is sticking out, that is going to be the R. Because if I go counterclockwise and the lowest priority is sticking back, it's S, but it's sticking out, so it's R. And what's its enantiomer? What would be the designation of its enantiomer? Would it be R or S? It's always going to be the opposite. My enantiomer is going to be the opposite stereochemistry. So if one enantiomer is R, the other one has to be S. If I look at the second molecule, I also have a chiral carbon. I'm going to assign priorities here. Bromine, then my ethyl, then my methyl, then my hydrogen. Oh my gosh, now I don't even have, my hydrogen is not sticking toward me and it's not sticking away from me. I literally have to mentally rotate it so that hydrogen is in back. This one turns out it's going to be the S enantiomer, so I go bromine to methyl, ethyl to methyl, looking straight up at the molecules or looking straight up here. That's going to be S. What's the enantiomer going to be? It's going to be R. Here's another molecule. Let's look for chiral carbons in this case. I only have one again. That is not chiral because it contains 2 methyl group. That's not chiral. This is the only one. This does not have chiral centers because I have a CH2 here. So if I look at this one, I do have my hydrogen sticking to the back, so that's good. Let's assign priority. Put on my ghost atoms. 2, 3, 4. So if I go 1 to 2 to 3, that's going to be clockwise. So this one is going to be R. The enantiomer is going to be S. If I look at this molecule down here, D, I have 1 chiral carbon. I have a methyl group sticking out in front, which means I have a hydrogen sticking out in back. Thank goodness. Let's assign priorities. My carbonyl carbon, my methylene carbon, my methyl group, and my hydrogen sticking way out in the back. So I go 1, 2, 3. That's counterclockwise. I have my lowest priority in the back, so I know that's going to be the R enantiomer. The enantiomer other one is going to be the S. If I look at this molecule and I look for chiral carbons, and I sort of go 1, 2, 3, and then my hydrogen going in the back would be 4. Okay. This one is going to be 1, 2, 3. That's going to be the R stereoisomer. But I also have another, on the same molecule, I have another chiral carbon. So we need to assign priorities again. 1, 2, 3. And I have a hydrogen. But this one times it's sticking out at me. So if I go 1, 2, 3 in this case, I notice that I'm going to be counterclockwise, but my hydrogen's going to be sticking out in front. So that's also going to be the R stereoisomer. If they are the same designation, this is going to be RR. So I'm going to have 2 stereocenters in this molecule, and this is going to be the RR stereoisomer. All right. Its enantiomer would be SS. To have the superimposable mirror image, I got to invert the stereochemistry at both stereocenters. Otherwise, they would not be enantiomers of each other. They would not be mirror images. Let's do this molecule. This looks crazy. Okay, so the first thing I'm going to do is I notice that I have a double bond here. So I'm literally going to identify the chiral carbon, and then I'm going to draw my ghost carbons. So I drew ghost carbons here. And now I'm going to start to work my way out from my chiral carbon, which is right in the center. And so if I go 1 atom out, I get a carbon, 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 and a carbon. They're all identical. Okay. Sometimes it's good to do this. Make a list, find out what the first atom is, and then move out 1 more atom. So if I move out 1 more atom from each of those, I'm starting over here on the left-hand side. I hit oxygen, oxygen, and there's a hydrogen attached there. So oxygen, oxygen, hydrogen. If I go to this atom, I get oxygen, oxygen, hydrogen, oxygen, oxygen, hydrogen. If I go to this atom, I got carbon, carbon, hydrogen right here. And if I go to this atom right here, I got carbon, carbon, and a hydrogen right there. Okay, so I notice I have to even go out further here to differentiate between these two and differentiate between these two. So I go out another carbon. So if I start over here on the left-hand side again, I notice I have a carbon attached here. And on this atom, on the oxygen, I have a CH, I have a C, and I have a C over here. So I got 2 carbons over here. And so in this case, that's highest priority over this one. So this would be my number 1 priority. This would be my number 2 priority. If I look at this next atom down here, and I look at, I have a HHH and I have an HHH, I have literally just hydrogen sticking off those carbons right there. If I look at this atom, I look at this carbon, I have a carbon sticking off of it. Because this is ghost here, I don't have anything sticking off this one, so I just have 1 carbon here. So I can start to prioritize things. So here's my highest priority. That is this carbon right here, this ligand. My second highest priority would be the ones with the oxygens and 1 carbon. Then the third highest priority would be this one down here at the bottom. My lowest priority would be number 4 here, and it's sticking out at me. So if I go counterclockwise, 1, 2, 3, because this is sticking out at me, I'm not going to call it S, I'm going to call it R. What's its enantiomer going to be? It's going to be S. So there's the nomenclature system for molecules that have chiral carbons.